presentation. Thank you.
Thank you. This is Arsan Majlisi. I'm a PhD structural civil engineering student at University of Texas at San Antonio. And my advisors are Dr. Montoya and Dr. Montemoros. In this presentation, I will be talking about the structural vulnerability of coastal bridges under extreme hurricane conditions and the equations available to predict the forces on these bridges. So as you all know, Hurricane Ivan and Hurricane Katrina had a severe effect on coastal bridges. 11 highway and railroad bridges were severely damaged along the US Gulf Coast. Superstructure collapse was caused by storm surge and wave action, and the costs and replacement of these bridges were, after Hurricane Katrina, were estimated to be about $1 billion. The characteristic of these bridges were that they were non-continuous concrete spans. They had inadequate or non-existent connections between the superstructure and bend caps, and the storm surge elevation approaching or exceeding the elevation of the span was one of the reasons that these bridges collapsed. In order to prevent the future failure of these kind of bridges, it is crucial to estimate the hydrodynamic loads. And there are existing approaches that we have been using in this study. The AASHTO from 2009, Douglas and Doe from 2006, and McConnell and Doe from 2003. These are the equations that we have been using in our study to calculate the forces on several bridges located in southern Louisiana. So the parameters that we will be focusing on in this study are the vertical forces and horizontal forces on the bridge superstructures. And we will be understanding how much difference is between different equations. Our objectives of our study is to provide an analysis technique that can accurately estimate the hydrodynamic loads, identify bridge configurations and type of bridge structures that are most susceptible to severe damages, propose practical structure equations that can be used for the current and future bridges, and to have a better understanding of the existing hydrodynamic equations that have been developed by several researchers. The parameters that we will be using in order to calculate forces on bridge superstructures are, as you can see in the figure, we will be using span length, span width, the wave height, initial water height, the difference between the bottom of the girder and the water level, and the overhang, railing height. These are all the parameters that have been taken into consideration to calculate the forces on bridge superstructure. So the method that we're using in this study is that we have been taking 500 bridges from southern Louisiana into consideration. It is our aim to understand the effect of inundation on these bridges, and it is assumed that Z, which is the difference between the bottom of the girders and the stormwater level, varies from -2 D, which is the height of the deck, to the value where the crest doesn't have any interaction with the bridge girders. And I also have to add that Z is negative if the stormwater level is above the bottom of the cross section. The figure that you're seeing right now is from a report from Louisiana Transportation Research Center. The yellow dots are showing the bridge spans that we have been taking into consideration. And this is one of the tables from the report of Louisiana Transportation Research Center. And they have been able to gather this information, the data for different bridges, and we have been using this data to calculate the forces. In this slide, you're seeing the vertical forces resulting from the equations that we had. bridge superstructures. The left one is from AASHTO, the middle one is from Kano and Doe equations, and the right one is the resulting forces from Douglas and Doe equations. As you can see, the x-axis is z divided by zeta. Z is the difference between the bottom of the girder and the water level, which when it's negative, it means that it's partially submerged. And zeta is the difference between the wave crest and the storm water level. So in a way, the x-axis is kind of showing the submergence ratio. And the y-axis is also showing the normalized vertical forces, which is the forces that are applied to the bridge superstructure divided by the weight of the deck. As you can see, the graph resulting from the AASHTO equations, it's the maximum vertical force reaches around 6.2 times the weight of the bridge deck, which is really high. And once the bridge gets submerged, the vertical force kind of increases too. And in the case of the Marconi equations, as you can see, only some parts of the graph are applied only between the x-axis is only between 0 and 1. And the reason for that is that the Marconi equations don't consider the cases which the bridge is submerged. So that's one of the problems of these equations, and they do not consider the slamming forces for the bridge superstructures. And this problem is also applied to the Douglas and Doe equations. They don't consider slamming forces, and they do not consider situations when the bridge superstructure is submerged. And as you can see in these figures, the results from the AASHTO equations are kind of higher than the resulting forces from the other two equations. And in this slide, you are seeing the horizontal forces applied to these bridge superstructure. Again, the McConnell and Douglas and Doe equations do not consider submerged bridges and slamming forces. And the behavior of the graph is kind of like different from the one from AASHTO. As you can see, the maximum horizontal force resulting from the AASHTO is much higher from the other two equations. So we could get to the point that, as seen in the figures from the AASHTO results, the vertical force is close to the weight of the bridge before inundation, but as soon as it's submerged, the vertical force significantly increases, which could be really dangerous according to those equations. It can be observed that the highest horizontal forces do not occur when the highest vertical forces happen, and vice versa. In the plots resulting from the Douglas and Doe equations, the maximum vertical force in some cases reaches 0.9 times the weight of the bridge, which shows superstructure is susceptible to failure, and the maximum horizontal force reaches 0.27 times the weight of the superstructure. According to the McConnell and Doe equations, the maximum vertical force in some cases is 0.9 times the weight of the bridge, which is similar to the Douglas and Doe equations, which again shows that the bridge superstructure is susceptible to failure, and the maximum horizontal force in these cases were 0.12 times the weight of the span superstructure. In order to conclude our study, I must mention that the comparison analysis demonstrated that the maximum vertical force during a hurricane event can become very high and possibly cause uplift of the superstructure. AASHTO equations revealed that the maximum vertical force reached 6.2 times the weight of the span superstructure for inundated cases. This study also suggests that because of a major difference resulting from the old and new equations, numerical investigation must be further developed to have a better understanding of what's going on in these bridges. And in order to do that and have a better understanding of the bridges, we have been working on numerical models these past few years, which you can see a video right now. In the first step, the bridge is getting inundated, the water level goes high, and then the wave starts. And the next video is another angle, which you can better see what is going on. And in this figure, the bridge becomes submerged and the wave starts. Yep, and these are a few of the works that we have been working on. Hopefully, in the next conferences, we will be able to present more interesting results considering the numerical methods that we have been using. And in the end, I would like to thank the people from Tran-SET for this opportunity. I'll be happy to answer any questions if it's possible.
Thank you so much, and yes, Arsalan, this is an excellent topic. I mean, I will open the floor and see if people have questions. I would like to hear from them first.
Sure.
If they don't, Arsalan, if you can show when you mentioned about AASHTO recommendations, in the railroad industry, the concrete decks, and you show some pictures at the beginning, excellent pictures of New Orleans and the concrete decks completely, yes. Well, they have even more like shorter decks, and I think you mentioned toward the end recommendations for the anchoring, but I don't know if you could expand more about what could be changing the anchoring of those spans to prevent what you just show here.
To be honest, we still haven't worked on that specifically, but we have been considering maybe members that could work in tension to prevent the bridge decks from uplifting or jumping away.
Thank you.